Hello everyone, welcome to the 8th episode of this series. In this video, we'll talk about properties of matrix multiplication. Last time, we found out that matrix multiplication violates one of the basic rules of traditional arithmetic, that it does not commute. What that means is that when you multiply two matrices, you have to be careful with the order of multiplication because reversing the order does not necessarily mean the same thing. In this video, we will explore other uh, traditional arithmetic properties, and we will see whether matrix algebra has them or not. The first operation I want to talk about is the operation of addition, and the first property we will look at is associativity. So this basically means that if you have three matrices, and if you look at the sum of those three matrices, then it does not matter which two matrices we add first. So we could add B plus C first and then add A to them, or we could add A plus B first and then add C to them. And they will give us exactly the same answer. And since this always happens, we say that matrix addition is associative. The next property is the commutativity of addition. Um, so remember, in the last video, we saw that matrix multiplication wasn't commutative at all. However, matrix addition is commutative. So if we have A plus B, that's the same as writing B plus A. And using associativity and commutativity of addition, we find out that we can actually arrange any sum in any possible way we want. Then the next thing I have on the menu is distributivity. So, in other words, multiplication distributes over addition. So that means that A times B plus C is AB plus AC, and B plus C times A is BA plus CA. Please do note carefully that when I am distributing this A on the right, I am writing BA and CA, not AB and not AC, because remember, multiplication is not commutative. Let's look at an exercise. So we're given two vectors, V and W, and we're given a matrix A. And we want to compute AV plus AW. So one way to do this could be, we multiply A with V and then we multiply A with W, and then we add the two resulting vectors together. However, we could just add V and W first, and then using distributivity, we could just compute A times V plus W. And we can add V and W together because they have the same size. So we do that. We first add V and W, we get 3, 3, and then we multiply the matrix A on the left to our resultant vector V plus W. And now because the width of the matrix A is the same as the height of the vector V plus W, this product is defined, and we can multiply each row by this column and then solve for it. And in this case, we get 909. The point of this exercise was that using distributivity in one way, we can actually save time. Okay, so the next operation I want to look at is multiplication. We've already seen that matrix multiplication is not commutative, but we'll see now that it is associative. In other words, if we have a product of three matrices, we can either multiply the first two first and then multiply them with the third one, or we can multiply the second and the third one first and then multiply them with the first one. So let's look at this exercise. So we are given two matrices A and B, and we have a vector C. You can also think of it as a 3 by 1 matrix, and we want to compute A times B times C and AB times C and verify that they are the same. Okay, so let's do that. So we first want to multiply the 3 by 3 matrix B with a 3 by 1 matrix C. So we're going to go row by row. So we're going to first multiply the first row with this column here. So we're going to multiply 1 with 1, 0 with 2, and 0 with 3, and that will give us 1 when we add all of these products together. Similarly, we'll multiply this second row with this column, and then the third row with this column, and we'll get 3 and 6. And then we're going to take this resultant vector 1, 3, 6, and we will multiply it with the 3 by 3 matrix A from the left. And then when we multiply it, using a similar process, we get our vector 25, 15, minus 6. On the other hand, we can first multiply A and B together. So it's a 3 by 3 matrix and a 3 by 3 matrix. So the resultant is also a 3 by 3 matrix. And then we take this resulting matrix and we multiply it with a 3 by 1 matrix or a 3 by 1 vector on the right. And now when you finish this matrix vector multiplication, you again get 25, 15, minus 6. So far, we've seen that matrix addition is both associative and commutative, but matrix multiplication is not commutative. However, it is associative. Can you think of a familiar arithmetic operation from your elementary school math, which is not associative? So in other words, between addition, subtraction, division, and multiplication, which arithmetic operation is not associative? Okay, so the next thing I want to talk about is the relationship between matrix multiplication and taking transposes. So it turns out that if you take a product of two matrices and then you take the transpose, that's the same as taking the product of the transpose of the individual matrices in the reverse order. So in this next exercise, we are going to verify that the transpose of AB is B transpose A transpose. Okay, so first we're going to multiply this 3 by 2 matrix with the 2 by 2 matrix, and we're going to again get a 3 by 2 matrix. So we multiply this 2, 1 with 1, 2, we get a 4. We multiply this 2, 1 with minus 1, 2, and we get a 0. And when I say multiply a row by another row, I mean the way in which we learned how to multiply a row and a column, of two matrices. Okay, and once we're done, our AB is this 3 by 2 matrix given by 4, 0, 1, 3, and 3 minus 3. And when we take the transpose, we end up getting a 2 by 3 matrix, which is 4, 1, 3, and 0, 3, minus 3. So remember that when we take the transpose, the rows and the columns get interchanged. On the other hand, we're going to take first transposes of matrix B and matrix A, and then we are going to multiply them in opposite order. So since my matrix B is 1, minus 1, 2, 2, its transpose is going to be 1, 2, minus 1, minus 2. So you take the rows and turn them into columns. And the transpose of A is going to be 2, minus 1, 3, and 1, 1, 0. So we take the first column and we make it the first row, and we take the second column and we make it the second row. And then we want to multiply B transpose with A transpose. So it's a product of a 2 by 2 matrix and a 2 by 3 matrix. So the resultant will be a 2 by 3 matrix. And you can verify that this is indeed 4, 1, 3, 0, 3, minus 3, and that is the same as AB transpose. And therefore, we have verified like the transpose multiplication relationship. So we saw some of these basic properties of transposes earlier, that transpose gets distributed over addition of matrices. A constant times transpose of a matrix is the same as the transpose of constant times that matrix, and the transpose of the transpose gives us back the original matrix. So we want to use these properties to solve for the value of B in terms of A in the following expression. So we're going to start with the equation that is given to us. This is A transpose plus 2B transpose whole transpose equal to 2A. So we can first take transpose. So the right hand side becomes 2A transpose and the left hand side becomes uh, A transpose plus 2B transpose uh, to hold to the transpose, and therefore it gets cancelled. So we get back the thing without without the outer transpose. Um, we can pull this 2 out in the next step by the second part of the theorem, because 2 is a constant. So we have A to the transpose plus 2B to the transpose equal to 2A to the transpose. And then we can subtract A transpose from both sides. And what we're left with is 2B transpose equal to A transpose. That gives us that B transpose is half times A transpose. In other words, transpose of half times A. And then you take transpose on both sides again, and we get B equal to half times the matrix A. And if you want to verify your solution, just plug back in B equal to half A in the original equation, and then you see that the left-hand side is the same as the right-hand side. Okay, so I want to spend the rest of the episode talking about things that aren't true. And we've already learned that matrix multiplication is not commutative. In other words, AB may not be equal to BA in most instances. So we learned that matrix multiplication is associative, but it's not commutative. So if we're given a product of a sequence of matrices, we can choose which of the immediate neighbors to multiply first. However, we cannot rearrange the matrices because of lack of commutativity, as we were able to do in the case of addition. So to make the next point, I want to start with an example. So we're given two matrices, 1 minus 1 minus 1 1 and 1 minus 1 1 minus 1. Both of these are 2 by 2 matrices, and neither of them are zero matrices. However, when you compute the product of these two matrices, you end up getting a zero matrix, because all the entries here are zero. So this is something that does not happen for real numbers, but it does happen for matrices, that you might have a product of matrices which is zero, but neither of the individual factor matrices are themselves zero. And a more general version of this phenomena is that if you have B equal to AC, if you have a matrix if you have a matrix A and you multiply on the right by two different matrices B and C, and you end up getting the same thing, that does not guarantee that B is the same as C. Of course, if B and C are the same, you're going to get the same product on both sides, but you might have different matrices being multiplied to A, but you might end up getting the same product. And like before, this is something that never happens for numbers. So in real numbers, if AB is equal to AC and we know that A is non-zero, then you can always cancel it and get B equal to C. So in this episode, we talked about arithmetic properties for matrices, and we saw that some of the classical properties hold and some of them don't. And with this, I would like to end this episode. I will see you guys soon in the next one. Until then, happy learning.